Any questions or problems with this? Okay, well. All right, so last time I sort of, I wanted to get the topological sort, so I skipped over a few things, so I'm going to be backtracking a little bit today before we make any more progress. And I want to start by making sure you remember how depth first search works. So we have depth first search on a directed graph. And to understand this, you've got to have the recursive structure of the depth first search algorithm in your head. So let's just go through an animation here and see what happens. So remember, depth first search, essentially, the depth first search method goes through all the, through the vertices in some order, and when it finds one that is unvisited, it calls explore. And explore is the recursive algorithm that actually does the search. So first thing that happens is depth first search picks out that as the starting point and calls explore. And as soon as a vertex is first visited, what explore does is give it a number, a pre-number. And our numbers start at 1, our times start at 1. Then what happens? What does depth first search do next after it's marked? Marked A is visited because it's yellow and given it a pre-number. Yeah?
It goes to the next node.
Okay, so it looks at its neighbors. It looks at the vertices that are reachable from it and visits each of them recursively. And you have to do them in some order, so we'll just do alphabetical order. So it'll decide, it'll go and look at B, and it sees that B is unvisited. So I'm going to mark that edge as black, meaning that we actually followed it. And since we're just visiting B, it gets a pre-number of 2. Now we're the explorer of A called explorer of B. Now what does B do? What does explorer of B do next? Okay, so it goes to either C or E next. In alphabetical order, we'll go to C. And it's unvisited, so we mark it visited and we give it a pre-number of 3. Okay? Now what are we going to do from there? We're explorer of A, depth first search called explorer of A called explorer of B called explorer of C. So we're 4 frames deep on the stack frame. What do we do from that place? What does explorer of C do? Okay?
That's a post number.
Well, okay, so it gets a post number, but why doesn't it explore anything out of it? There is nothing out of it. There's nowhere to get to from C. So once there's no place else to try, you get a post number. So C gets that post number of 4. And then we return from explorer C back to explorer B. Okay? Now explorer B has already gone towards C. The only other place to look is E, so it does explorer E. That's not visited. So it gets a pre-number of 5. Okay, now what happens? Okay, it'll try to go to C, but that's already been visited. I'm sort of coloring things differently than I did on other examples, but how can we tell that C's been visited? Well, it doesn't. It has a post number, but that's not how you know it's been. That's one way. But what's the foolproof way of knowing it's been visited? It'll have a visited flag. That's not visit. It'll be marked visited. It's not. You can't tell that visually up here. It's the pre-number that really cinches it. Okay, it'll definitely have a pre-number that's been visited. So we back out of that. And I'll mark that orange, meaning we didn't actually follow that edge. Now we'll try to go the other direction to D. D has been visited, so we mark it. It gets a pre-number of 6. Only one way out, we try to go to B. Now notice B doesn't have a post number, but it does have a pre-number, so we know it's been visited, so that turns red, orange. And now there's nowhere else to explore out of D, so it gets a post number. We return to explorer B, nowhere to go there, so it gets a post number. We back out to explorer B, nowhere to go. it gets a post number. We go to A, we try that, A to D, that doesn't work out, so we get a post number on A. And at that point, we return back to depth first search. And depth first search is going to iterate through the vertices. It'll look at B, visited, C's been visited, D's been visited, E's been visited, F hasn't been visited. So depth first search will start things up again by calling explore F, which gets the next number, 11. G gets 12, 13, and 14. So that is what happens when you do a depth first search on a directed graph. Now, are there any questions about that? This is something that you need to get good at, to be able to do in your head as easily as I can do it in my head. Yeah?
If there are weights, do you like choose the cheapest way to go, or?
No, if there are weights don't matter to depth first search, so you just ignore the weights. On the edges, yeah?
So the mechanism that gets, that starts up on F, there's just one loop that's looping through all of.
Right, the depth first search algorithm has a loop that's just iterating through the vertices. And when it finds an unvisited vertex, it calls explore on that vertex. Then when explore returns, a bunch of vertices have been marked visited. So that's why it doesn't call explore on every vertex necessarily.
So you have to have like some sort of structure that holds them just like linearly as opposed to having to traverse through the graph?
Well, you need to have your graph represented as either an adjacency matrix or a adjacency list. If it's a matrix, you're just, the vertices are indexes into that thing. Well, actually, you've got the visited array is what you're iterating over. So, yeah.
If the pre-search is the number we base it off, remind me what the post-search number is for. Why you need that?
Well, actually, the pre-number is the least interesting of the two. The post number, we use it, for example, to linearize DAGs. This isn't a DAG. But we'll look at DAGs in a minute. Yep.
And does it matter like which node you start with?
Does not matter where you start. I mean, it matters, where you start matters in that, if we started at B, it would have gotten a pre-number of 1. The numbers would be different, but we could still do a depth first search no matter where you start. Yeah?
So at the topological, you still need to like calculate the least weighty path or what have you, but does topological just prevent you from like exploring these long routes that you know aren't gonna...
Well, you're asking about topological sort, which is what I ended on last time, but we're not topologically sorting this graph because it's not a DAG. Notice it has a cycle. So if I don't answer that question a little bit in the future, let me know again. Okay, now one thing you can do when you do a depth first search is you can classify the edges that were discovered. Notice you end up considering every edge in the depth first search algorithm. So the black edges, we call those tree edges. So if you look at the black edges, they form a tree, a forest of trees. So we got one tree rooted at A and another tree rooted at F. So the edges that actually followed formed a tree, and they're called tree edges. Now, if we did the search a different way, we'd have different tree edges. So it's not like, being a tree edge is not a property of the graph, it's a property of the depth first search that you did on the graph. The orange edges can be classified as back edges, forward edges, or cross edges, depending on where they go. So a back edge goes to an ancestor in the tree. So why is DB a back edge? Why is that orange edge DB a back edge? Yeah?
Because B is not a leaf node?
Well, it's not because B is not a leaf node. It's why.
By the time you get to D, B's already been visited, so you're going backwards in the tree.
Okay, so he said, I'll paraphrase what he said. Think of B. One of B's children in the tree, look at the black tree. One of B's children is E, and one of E's children is D. So we can think of D as a grandchild of B. So an edge that goes to an ancestor in that sense, it goes from the grandchild to the grandparent, is a back edge. Okay, a forward edge goes to a descendant in the tree. So it says here that AD is a forward edge. See why that is? Right? It goes from basically goes from a great-grandparent to a great-grandchild. It goes forward in the tree. That's a forward edge. And anything else is a cross edge. So EC, for example, goes from, it doesn't, it goes from a sibling to a sibling in this case. It doesn't go to either a descendant or an ancestor. So that's called a cross edge, and so is GE. Now, how can you identify these edges? Clearly, you can figure out what the tree edges are because you identify them as you traverse the tree. But how can you tell? How can you identify the other edges? And I'll answer my own question. You can do it by looking at the pattern of the pre-post numbers. So suppose you have an edge from U to V and you want to classify it. You can classify it by looking for a pattern like this, one of these patterns. And let me tell you what the pattern means. Think of these brackets as that's the pre-number for U, that's the post number for U. The pre-number for V, the post number for V. And the numbers are increasing in this order. So this says that the pre and post number for V are contained inside the pre and post number for U. So maybe U is 2 and 10, and V is 5 and 6, so they're nested. So if you see that pattern, what kind of edges are we talking about?
Back edge.
Okay, let's see, a back edge. So DB, we've got
6 and 7 is 2 and 9.
6 and 7 is inside 2 and 9. That's not what this pattern would say. This pattern would say 6 and 7 is contained in 2 and 9. You got to. It depends on what the endpoints are. So that back edge, DB, is the edge we're going to, B, brackets, the vertex we're going to, the post times bracket, the ones for B.
Tree edge?
Right, so tree edges have this pattern. And also forward edges do, it turns out. So tree edges and forward edges, the post numbers nest like that. And then for back edges, they nest sort of the opposite way. And then for cross edges, they're just distinct. Yeah?
Is there a way to differentiate if it's a tree or a forward?
Okay, how do you differentiate whether it's a tree or a forward? Yeah?
Once you've already marked the tree edges, so by default.
Okay, so what he said, wouldn't you have already marked the tree edges? Basically, if you want to differentiate tree and forward edges, as you successfully follow an edge, you need to remember that. Yeah?
Could you also do, if either the pre's or the posts are only one apart, then is it tree edge if it also follows the tree/forward edge type?
I don't think being one apart would.
Because you've got 2 and 3 on the pre for BC, and you've got 8 and 9 apart on the BE edge, and those are both following the tree forward, and also the distance between the two, either pre or post.
Yeah, what does it mean if the post numbers are one apart?
That you went one node back when you were in your...
Yeah, well, there'll be one, pre and post are one apart if it's a leaf node in the search tree.
Right.
Yeah,
So
I'd have to stare at this and look at other examples.
Okay.
So, yeah.
I don't think it would apply because look at like 2 to 5, that's not one apart, but that's still a...
2 to 5, you mean?
the posts
B
on
to
that
E.
one are one apart, 8 and 9. It doesn't matter. It's
Okay.
yeah, it's academic.
Yeah.
So I guess I'm not seeing this, because looking at D, 6 and 7, it's in between 1 and 10 on A, it's in between 2 and 9 on B, and it's in between 6 and 8 on B. So I guess I'm just not seeing what that pattern of is within the...
Okay, let's look at the edge. So you have to look at the edge from A to D. Okay, so in that case, A is playing the role of U, and D is playing the role of V. Okay, so what nesting pattern do we have? Looks like the U post times bracket, the V post times in that case.
Okay.
There, so we got a forward edge. On the other hand, what's the other one you asked about, like D to B?
Yeah.
Well, that's going to be another forward edge. It's bracketed the same way.
D to B is a
But
back.
it's a back edge.
Oh, okay, right. Okay, D to B is the back edge, so it's nested the opposite way.
But it's also nested.
Yeah.
Is there a way to determine? Oh, never mind. So we have to look at what points to what.
You have to look at what points to
Oh,
what.
I see. Okay, I got it.
You can't just arbitrarily say U and D are two vertices. You got to know which edge goes to which place.
Okay, I see.
And
Yeah.
where you get forward and back edges, that depends on like where you start in the graph. If you started
Oh, absolutely.
F, you would have had different back edges and forward edges. than
Right.
you started
So
there.
these, it's not like this is a property of the graph again. It's a property of the search. But there is one edge, one type of edge that's interesting to discover. Back edges. Okay?
Cycles.
Back edges are cycles. So if there are no back edges, if you find no back edges during a search, it's a DAG. It's, if you find no back, yeah. First, also, this is only interesting for directed graphs. If you're doing a depth first search of a directed graph and uncover no back edges, then you know it's acyclic.
Always.
Yeah, always. You have to have a back edge to have a cycle. You look at all the other edges, the orange edges that aren't back edges. They don't create cycles. And in fact, you don't have to do the analysis and get all the pre and post times and then figure out whether or not there was a back edge. How can you detect a back edge as you're searching?
Where are you running?
Yeah.
When the child knows has already been visited, doesn't that mean that you've already gone through it?
Okay. So think about when we're doing the depth first search, we go from A to B to E to D, and then we find out that B has already been visited. Okay? That doesn't necessarily mean there's a cycle. So think about the depth first search that finished all this, and then we go from F to G to E, and E's already been visited. That's not a cycle. So specifically, what is it? How do you know that it's a cycle? It's been visited. There's something else has to be true. Yeah.
And the visited node points to where you just came from?
Sits in the same.
No, not that. So, yeah.
So could you just look in the stack and see whether or not B's in the stack?
Well, we don't have to look in the stack. How can we tell? So when you find this edge that goes from D to B, and you notice that B has already been visited, how do you know it's a cycle?
Can you look at the pre-number?
Well, you know there'll be a pre-number. Okay, and in fact that pre-number will be smaller than D's pre-number because B's already been visited, it was visited first. Yeah?
This is a little bit off topic, but I'm having a hard time seeing how, it makes sense how D and B is a back edge, like how it makes a cyclic graph. But with the UV format where U is pre and B is post, 7.
No. U has pre and post number. U is a vertex. It has a pre-number and a post number. V is a vertex. It has a pre-number and a post number. Don't think of U and V as being pre and post pairs. Okay, so how can we tell as we're searching, when you go to something you've already visited, that is a cycle? Get behind you.
If it's as for searching, the one that, once we get to B, there won't be a post number?
Exactly. If you encounter a vertex that has been visited, but does not yet have a post number, then you know you've closed a cycle. Because think about it. If you've already visited, so think of B. You already visited B, so it's going to have a smaller pre-number than D. And if it doesn't have a post number yet, it's going to end up with a higher post number than D will. And so you're in back edge territory. So when you encounter a visited vertex that does not have a post number, you can tell right there that you got a cycle. So if you want to algorithm a search for cycles, that'd be the simplest way, like the asimple way. Okay? Any other questions about this? Okay, so here's what I just said, the cycle property. That there's a cycle if and only if the depth first search reveals a back edge. And I basically just, I won't, you can look at that later, but just repeats a little more formally the argument I just made. All right, that's just illustrating the cycle. So this was DAGs. So we looked at depth first search on DAGs, and we talked about what they were for. I'm not going to repeat that. We're going to look at some examples later. Linearization is making a list of vertexes. So you make a list of vertices such that no vertex has an edge to a vertex that occurs earlier in the list. So linearization of this would have the property that A has to come before B and D, because A has edges to B and D. B has to come before E. D has to come before B and E, and so on. Now clearly you couldn't do that if there was a cycle. If there's not a cycle, you can. And there are multiple ways to do it. So we can linearize or topologically sort that graph. These are the only three ways to do it. In this graph, there's one source, which is A, meaning the source has no edges in. And there are two sinks, C and F, because they have no edges out. Of course, you always have to have at least one source in a DAG and at least one sink. You can have any number. Now, what was our algorithm for linearizing, for topologically sorting the DAG? I'll read the answer from the slide. Yeah?
Do a depth first search with pre and post numbers, and then sort the post numbers in descending order.
Okay? So, and now, what this says is that in a DAG, every edge leads to a vertex with the lower post time. No matter how I do the depth first search, every edge will lead to a vertex with the lower post time. So the sink, there'll be some sink that has the highest post time of all. Now, why does that work? How can we know that? Yeah.
From what we're talking about on the last example, the only time you have a greater post number is if it's a back edge, and because it's acyclic, there are no back edges.
Okay, so he's making the argument saying it's acyclic, there are no back edges, and so you don't see that pattern. Let's talk about it without talking about back edges. Like take that edge, say from B to E. How do we know that B will have a higher post time than E? Yeah?
Because E will be returned to before B is.
What do you mean return to?
E will get its pre-number, check for more nodes, and get its post number before you return to B to give it its post number, right?
Okay, that's essentially right. Imagine a depth first search. Will you visit B or E first in a depth first search? Okay, is that right? Yeah.
Then you go AD, then E.
Yeah.
Then you go back, you go B.
Yeah, you could visit anything first. Depth first search, the algorithm, we're doing things in alphabetical order, but it doesn't have to. I mean, E could be the very first vertex visited, period. Now, so let's assume, what if B is visited before E? How do we know that B will end up with a higher post time? Yeah?
Because nothing from the children of E point back to B.
Right. So B gets a pre-time, then E gets a higher pre-time, and then we explore from E. And explore from E cannot possibly go back to B. So this was DAGs. And so that clump there of E, C, G, and F will all get post times before B gets a post time. On the other hand, what if you visit E first? Yeah?
You'll never get to B. Well, you will after you
Yeah.
finish exploring.
So you explore out of E, you'll finish that up, you'll get a post time, and then sometime in the future, B will get visited and it'll get a post time. So either way, whether you visit B or E first, B gets the higher post time. So that gives us an algorithm for topologically sorting. You just compute the post times and then sort in descending order of post time. And it doesn't matter what happens as you search, where you start, how you make arbitrary choices. It always works out. All right, and I did this last time, so this is just 2 examples. There's one way of making arbitrary choices. And if you notice, every edge leads from a higher post time to a lower post time. Then we can, that corresponds to one topological sort. And we can do it in a different order. We can make our arbitrary choices a different way. The pre and post numbers are different, but still every edge leads from a higher post time to a lower post time. Yeah?
So how do you find the final linearization? Do you just look for the highest post time?
Well, you basically sort the vertices by post time in descending order. So you just associate the post time with the vertex and sort in descending order. We'll look at another way to do it shortly. Okay? So that's topological sorting, which is if you're ever have an algorithm on a DAG, the first thing you do is topologically sort it. Okay? I want to say that again. I don't want to stand on the desk again today. But if you are designing an algorithm for a DAG, start by topologically sorting it. Okay? And we'll look at examples. All right. Now, what's the complexity of topological sort? Now, one thing I skipped over that I'll be going back to is to analyze the complexity of depth first search. And what it turns out is that the complexity of depth first search it's linear in the sense that the time required by depth first search is proportional to the size of the graph data structure. So if your graph is a matrix, it's going to be V squared. If your graph is if your graph is represented with a matrix, the time for depth first search is V squared. If you're using an adjacency list, then it's V plus E. So it's just proportional to the size of the data structure. So suppose that what we do is a depth first search to get the post times, and then we do a merge sort using the post times as the thing we're sorting on for each vertex. What would be the complexity of that? So suppose we're represented as a matrix, yeah?
Whatever the complexity of depth first search was, plus n log n.
Okay, well, not n log n.
So,
What are we sorting?
oh, yeah,
Yeah, V log V.
v log v.
Right. So you're just so used to saying,
Yeah.
the sorting is n log n. Well, that's if there's n elements. In this case, there's V things we're sorting, so it's V log V. No big deal. So in a matrix, it's O of V squared, we'll see. That's the size of the representation. You have to look at every bit of the representation. So that's depth first search, plus the cost of the sort. That gives us V squared, that's the best you can do in any graph algorithm that has to look at every bit of look at every edge, every vertex, if it's a matrix. For a list, there's depth first search, plus the sort. And we get this term, V log V plus E. That's kind of annoying, because it could be worse than, V log V is it could be bigger than V plus E. V log V is bigger than V plus E, so it seems like we could improve. Yeah?
Are you talking about sorting the vertices in alphabetical order?
No.
Before you do the...
No, I'm not talking about sorting the vertices in alphabetical order. I'm talking about running depth first search, associating the post times with the vertices, and sorting on post times.
Couldn't you just include the sorting in depth first search?
Well, that's where we're headed. Yeah?
I mean, we can improve on that.
Yeah, we can improve on that. Right. So I'd like to have an order of V plus E a topological sort. I'd like to, you know, to improve the cost of sorting. And here's the thing. Imagine if we didn't bother with pre-times. We just recorded the post times. So when we're all done, we would have, A would have 14, well actually A would not have 14 if we just recorded post times, and we just have 7. So we'd have these vertices numbered 1 through 7. Rather than sort them after we're done, what could you do as soon as you discover a post time? What can you do? You're going to have some vertex that gets a post time of 1. What do you do with it? Yeah.
Put it in an array?
Yeah, put it at the, you put it at the end of, you have some array that's going to be holding the sorted vertices.
Size V.
So, of size V. When you find out that, what would have a post time of 1?
F. No, C.
C has the lowest post time. So if we're skipping the pre-times, it would have a post time of 1. So you put, as soon as you find a post time, you stick it at the end of the array. The next one that gets a post time, you stick it next to that element at the end of the array. So you just fill in the array backwards. As you discover post times, the last one you stick in the array would be A, it'd be at the beginning. You've got it sorted with no extra cost. You don't have to do a merge sort. So now the complexity of topological sort is just the same as for depth first search, which is what I was after.
It's still B squared for a matrix, right?
Yeah, it'd still be V squared for a matrix, but that's the best you can do with a matrix algorithm. If the algorithm requires you to, you know, to completely consume the data structure, because it's V squared big. You've got to look at the entire data structure, it's going to be V squared. Okay? So topological sort's efficient, which is good, because you got to do it before you do a DAG algorithm. So this is just this is an illustration that if we just recorded post times, that's what you would get. And basically, as you discover them, you just fill in the array. Now there is another way to linearize, which is essentially you look at the data structure and find a sink. I mean a source rather, and you take it out of the graph, and that becomes the first element. That's the first thing in topological order. So if we did it. Let's see, we take A out, now we look for a source. What's a source?
D.
You take it out. B is a source. Now you got choice. It's either 2 sources, so you pick one.
G.
I did G. And now you got 2 sources, so you pick one. And then only one left. So that's another way. You sort of deconstruct the graph. So to make that efficient, you've got to have an efficient way of knowing, of identifying the sources. That doesn't involve searching every vertex. I won't. Let's stick with. I'm not going to talk in more detail about that. I just want to make this observation. I recommend you use the post times to sort. Yeah.
So I mean, doing it that way, you could end up with something different from using the post time.
Okay, saying, okay, there were arbitrary choices we had to make, which means that we might not get the same answer that we get with the post-time thing. But in the post-time version, there's arbitrary choices you make. So basically, depending on how you make arbitrary choices, how you flip a coin, you'll get different linearizations. They all have the same property. They're all linearizations. Yeah?
How do you determine whether your B or D goes first, though? Because it starts out, if you go back to the graph. So like, D clearly has to go next, but A pointing to B and D before this. So
Right.
Yeah.
So you're asking how to efficiently determine that D is now the source?
Yeah, not knowing that I don't go to D next, because D should go next.
Well, you'd have to, I mean, you could at least just search the data structure and find out that D has no edges out of it. That would be too inefficient. So I don't want to go into exactly how you efficiently determine what the sources are, but assuming that you could efficiently determine what the sources are. That's how that would work. Okay, so that's just another way to do it. Now, we're back where we ended last time. Algorithms on DAGs. you will not see a DAG algorithm in this class that does not follow into this category. Okay? So an algorithm on DAG, you start by topologically sorting the DAG, and then doing some sort of computation on each vertex in sorted order. Now, when I say some kind of computation, I do not mean if you find yourself saying, okay, I will topologically sort the DAG, and then I will look at each vertex in topological order, and I will do a depth-first search beginning with it, or I'll make a recursive call beginning with it. That's not what I have in mind. I have a simple computation. Okay? And I'll show you examples. Not a searching, not a recursion. Or the other version is you'll topologically sort and go backwards through it. Now, for some reason, despite the fact that I even stand on the table to make the point, students, I look at what they're doing in CADIS and it's just, what's going on here? They're not topologically sorting. Okay? It's similar with other things. When I talk about the majority algorithm, and I look and I see nested loops doing an n-squared algorithm taking more than 16 seconds on CADIS. Why aren't they using the majority algorithm? I said, use the majority algorithm. And the only conclusion I can make is that some students want to separate between sort of the completely theoretical algorithm class that they got to get through and real programs. And that the algorithm class has you learn nothing in the algorithm class that is useful in the real world. That's just nuts. Stuff is very useful in the real world. So don't dismiss what what you hear here. It really works. It makes a difference. A lot of these CADIS problems are constructed so that if you don't use the efficient algorithm, you run out of time, even if you're using C++. Okay, so let's look in more detail at some of these examples we looked at the end last time. So this is supposed to represent a spreadsheet. So we've got these cells in the spreadsheet, 6 cells, A, B, C, D, E, and F. And each cell contains, A contains the number 2. E contains the number 5. D contains the formula A plus E. B contains the formula A times D. F contains the formula D times E, and C contains the formula B times F. You see how that works? So what the cell contains is inside it. So this just says multiply the things that point at me. The thing outside the cell is the actual value that's displayed and the value that's used in computations. So you can see if a cell contains a 2, you would display 2 as its value. If the cell contains 5, you would display 5 as its value. If the cell says add A and E, if A is 2 and E is 5, you would display 7 as the value of D. And so there's the update problem on a spreadsheet, which is suppose you put something new in a cell. Suppose you store 7 in A. You've got to update the display. You've got to recalculate the display value of some of the vertices. How do you do that efficiently? And it's a DAG problem. So we linearize it. And this is a simple computation. For each vertex, in sorted order, look up the values of the predecessors, then compute and save the new value. That's the right order to do the update. Now that would say that this would tell you how to update every single vertex. In reality, you can be more efficient than that and just update the ones that need to be updated. But why does that work? Forget about the optimization. How can we know that we don't have to recursively do anything, we don't have to do any searching? How do we know that if we do the updates in topological order that we're okay? I mean, what we want to avoid, we don't want to start by recomputing C. What would happen if let's say we changed A to something and we started by recomputing C? What would go wrong? Yeah?
still have the old values for B and F.
Right, we haven't recomputed B and F yet. We want to make sure we don't do C until we've done B and F. And we don't do B and F until we've done, we don't do B until we've recomputed B and A. And so on. So what does the topological sort have anything to do with here? Yeah?
It represents like the dependencies between them. So,
Okay. So it sort of distills down the dependencies. Yeah?
It'd be the order that the thing should be computed in.
The topological sort gives you the order in which you do the computations. Because what comes first are the sources. And what comes last are the sinks. So we compute from the sources to the sinks. When we compute a vertex, the topological sort, when we consider D, we're guaranteed that both of its children have been recomputed already. That's just what the topological sort guarantees. If there's an edge from A to D, and so that A will come before D in the topological sort. All of any vertice's predecessors will come before it in the topological sort. Now, if A changes, we don't need to recalculate E. Yeah?
So when you linearize versus the original A, how do you do that using the other method, like more generically when you don't use the pre and post? Because when you're, I don't know, in my head, how you would identify a source, I would have to I definitely would be to iterate through it and see if anything is routing into it.
Yeah, well, basically I said I wouldn't do that, but what you would do is you would pre-process the graph.
Right.
You would count how many vertices were into each vertex and create a priority queue. That's one way to do it.
So that you just wouldn't include E. I'm sorry. So in relation to
yeah, well, let me go back to my original thing. I'll talk to you after class about it. I really don't want to get into the details of that algorithm. I might even have it as a problem. So. Okay. How would we decide? How could we figure out, knowing that A has changes, what would be a fast way to find out what needs to be updated? Yeah.
Anything that comes from A.
Okay, anything you can reach from A. How can you quickly determine what's reachable from A? Yeah?
Post numbers that are one away from.
No, probably not from the post numbers. What would be an algorithm that we know? Yeah?
Reverse topological?
No. We've already sorted it. What algorithm? It has a name. It tells you whether, you start somewhere and you can visit everything reachable from it. Yeah? Not depth first search. That visits everything. Yeah? Not breadth first search. Explore. Explorer can tell you. But I'm not really worried about that part of it. I just want to update things in the right order. So, let's suppose A changes to a 7. These are the vertices reachable from A in topological order. So that tells us what order to evaluate them in. And notice a simple computation. What's it take to recompute a node? You have to know the values of its predecessors, and then you do an operation. Well, in this case, there are no predecessors, and so the new value of A is just 7, because it's a constant. Now it says to do D next. Okay? You look at the values of its predecessors, and you add them. How do we know the predecessors' values have already been recomputed, if necessary? What guarantees? Yeah?
The fact that we're just topological.
Right. We're processing in topological order. So we add the 5 and the 7, secure the knowledge they've dealt with, we get a 12. Then it says to do F next. So we've got to multiply the 12 and the 5. Then it says to do B next. There we multiply the 12 and the 7. And then it says to do C. We add the 84 and the 60. Topological sort let us do things in exactly the right order. Notice what I mean by simple computation. I look at the values of my predecessors and apply the operation. I don't have to search. I don't do anything except look at my predecessor's values and deal with those values. That's what I mean by simple computation. Yeah?
What about E? Like, does Is E go before A or after A?
Well, if I'd included E in the topological sort, it would have been reevaluated. It wouldn't have changed. So obviously, in a real spreadsheet, if you've got thousands of cells, you don't reevaluate every cell. You just reevaluate the ones that are affected by the change. You can detect what's affected by the change with the call to explore. You deal with the vertices that were revealed in the call to explore in topological order. Yeah?
So when you're doing the depth first search, how does it know that D is the first one in the order of the graph to go to?
Well, when you're doing the depth first search, well, D isn't first, A is first.
Well, from A.
Well, how did D get there in topological? I mean, how did D come before B, F, and C? Because it had a higher post time. So topological sort gives us exactly the property we want. If there's an edge from a vertex to from vertex X to vertex Y, X will come before Y in the sort. In this case, that's great. If we process the vertices in topological order, we're good. If we don't, if we do it backwards, you get all kinds of garbage. Now, there's one fine point here. How do you find the predecessors? Yeah?
Did you do a depth first search on the whole graph and then reverse it?
Well, we don't want to do another depth first search. I mean, what's the problem with finding predecessors in a grid?
Predecessors reverse the edge. Like,
Okay, let me just draw you a picture here. Okay, suppose we have this graph here. We got this vertex A points to B, points to C, and points to D. So if it's an adjacency matrix, we got A, B, C, D, A, B, C, D. What entries would be in the matrix? This is the from, this is the to. So there's an edge from A to B, so there would be an edge there. There's one from A to C. There's one from B to D and one from C to D. Okay? So what would you have to do to find all the edges out of a vertex? Like find all the edges out of vertex A? You just iterate across here, looking for ones. How do you find all the edges into something? Like all the edges into D. How would you do that? You just do a column. So that's equally efficient. So no problem identifying predecessors. Yeah?
Except for on the last graph we had something that wasn't like the E was separate, right?
So you got E, and now there's an edge from E to C. That's no problem. But what if you have an adjacency? I'm going to, just to save time, I want to get rid of that's the right thing. How do you get rid of it?
just click it again. Is that not working?
Okay. Yeah. Obviously, I could benefit from some straight edges here. What does the adjacency list representation look like?
So you're throwing back edges or forward edges?
Well, that's the question. Adjacency lists, just each thing under A is going to be an edge out of A. So what's going to be stored in A's linked list?
B and C.
An edge to B, an edge to C. B is going to have a linked list like this, B to D, and then we're going to have C to D, and then that's null. So how do you find the edges out of something, like out of A?
You just go to A and then top.
You go to A and then follow down. How do you find the edges into A, or into D? That looks inefficient, doesn't it? You've got to basically consume the entire data structure to find the Ds.
Like you just throw backward edges.
So the typical solution is, if you're doing the kind of DAG algorithm where you've got to look at predecessors, you want to do what's called reverse the graph. So before you start, you do the topological sort in the original graph, then reverse it, because you want to have an efficient way to access predecessors. Not, you don't need an efficient way to get successors. So what does it mean? How do you reverse a graph? How complex is that operation? Boy, this is hard.
Should have just saved it.
Yeah. Okay. How do I reverse that adjacency structure, that adjacency list over there? You know, I'd start by creating, this is the reverse over here. So I'm going to reverse all the edges. I just come over here to A and I iterate down. And I see, okay, this stores an edge from A to B, so that needs to be turned into an edge.
I can't see where you're pointing.
Okay. I iterate through that. I find A, I go down its list, and every time I find, when I see that there's an edge from A to B, I store it over here as an edge from B to A. So I find it, I immediately add the edge. Now I come down here and see there was an edge from A to C, so I want to add an edge from C to A. So I add it over here. Okay, I keep coming, I see there's an edge from B to D, so what will I add? There's that edge. And then I see there was an edge from C to D. What do I do? Okay, I got to add an edge here. But what I don't want to do is go all the way to the end of this list and add it to the end, if it's a linked list, because that would take too long. What's a better thing to do? Just stick it in the middle here. Stick it at the beginning. What did that go to? C. Now, if you're using an array list for this purpose, which then you just add it to the end. It doesn't matter. Okay, so it's an efficient operation. I just have to walk through this entire data structure and add the edges over here. So the time it takes is proportional to the size of the data structure. So reversing is efficient. Yeah.
Is reversing more efficient on a matrix?
He asked, is reversing more efficient on a matrix? You don't have to reverse a matrix. Because the reason you reverse the structure is so you can get efficient, you efficiently identify the predecessors. So on a matrix, you just go down the column. But you almost never use a matrix. Don't use a matrix on the autosync problem. It would be too big. Yeah?
Why do we have to either use a list or a matrix? Why can't we just have a set of nodes that reference other nodes?
Okay. Let's hold that question. Let's take a break and we'll see. We'll think about that alternative. start again. All right, so we had the question. We got this graph here. Here's the adjacency list. Alternative is an adjacency matrix. Why do it that way at all? Why not just use objects in memory? So we'll store our graph this way. We'll have A be an object that has a reference. Just store it isomorphically to that thing up there. Just have objects and references in memory, just shaped like a graph. Okay? Why bother with lists and arrays and matrices and such? Yeah?
I mean, you need a way to organize it and iterate through it.
Well, he said we got to have some way to organize it and... I mean, why is this by itself not enough? Yeah?
Isn't it like anytime you wanted to know something about it, you have to walk through it again?
Okay, she said, are we going to have to walk through it to find out anything about it? I mean, what's the most fundamental thing you want to be able to do?
See how many nodes there are.
All right. So see how many vertices there are. Right? This doesn't exactly help with that. You could store it on the side. You could have this plus you could store 4 as its size. But what if I wanted to find the vertices out of edge A, out of vertex A? I wanted to find the vertices I can reach from A. How would I find those edges? Yeah.
So if you store all the nodes in a hash set.
Okay. So you wanna do this. And this will be A, and this will be C, and B, C, and D, right?
And then you could hash on A.
So a hash map is basically like an array. If we assume that our vertices, the names of our vertices are array indexes, then we use an array. If we decide that if our array indexes are strings, we have, that right there becomes a hash set, a hash map. Okay? What's this starting to look like here?
Adjacency list.
It looks a lot like the adjacency list, just a little more convoluted. So that problem, you got to have direct access to each vertex. This essentially becomes a lesser form of an adjacency list. Okay, let me emphasize that point I made. Just for ease of discussion, we're assuming that our vertex names, A, B, C, and D, translate into array indexes. If they don't, such as in Cass problem this week, rather than represent your graph as an adjacency list, where the spine is an array, that spine becomes a hash table. So it's just a hash table that maps what to what. What's the key? If we're using an adjacency list representation, and you got to use a hash table, what's the hash table map? What's the key? What's the value? Yeah?
City name to a vertex.
Okay. So he said it would map a city name. It would map the vertex name to what? Yeah?
Element list or set or...
Yeah, a list or a set of vertex names. It's the same, you'd use the same picture for it. It just maps it in a different way. So it's no harder than using an array. It's just you use a dictionary instead of an array if your vertex names aren't convenient to use as indexes. Okay, so back to PowerPoint.
So to update, you run Explore and then iterate through and...
Yeah, okay, so to summarize, to figure out what vertices need to be updated when A changes, you can do a call to explore, and that will identify that A, D, B, F, and C need to be updated. And then you deal with those things in topological order. You do a topological sort of the graph, and then you just deal with the vertices you have to deal with in order.
So V plus C, and then you do it over.
Do what over?
You process the nodes in order.
One Explorer tells you that every vertex except E has to be updated. And then you update them in order, in topological order. Yeah?
So if for some reason you wanted to to change D to a minus, would you just do the explore on D and then just change everything else from there?
Yeah, if you change D to a minus, you would do an explore from D. You find out that D, B, F, and C have to be updated, and you would update them in topological order. Yeah?
I'm confused because in order to update D, don't we have to find its predecessors?
Yeah, you have to, so I'm assuming the graph has been reversed so you can find D's predecessors. To evaluate D, you got to be able to efficiently find A and E or its predecessors. That's why you reverse the graph. Any other questions? So what's the creative part of designing a DAG algorithm? Is it remembering to topologically sort it? Is that the creative spark? No. That should be natural. Where does the creative spark come in?
How to process the vertexes?
Yeah. How to process the vertices. What do you do at each vertex? In what order you do it. So let's look at another example. Okay. So I want to know, we looked at this last time too, number of paths leading from a source to a vertex. And I've already labeled it with the answers. So this is number of paths leading from A to every other vertex. So we just say that the number of ways to get to A is 1. There's 2 ways to get to B. What are they? You go A to B directly or go via D. So 2 ways to get to B from A. There's 6 ways, it turns out, to get to A from F. So we want to compute this. So what's the creative spark here? What simple computation could you do to each vertex, assuming you do it in the right order, that would tell you the answer, the creative spark? You want to say?
You would just add the paths of the 2 predecessors.
Okay, you look at your predecessors and add up their values. So if there's, look at G. If there's 3 ways to get from A to C, and there's 3 ways to get from A to E, then there's 6 ways to get from A to G. You either take one of the 3 paths that lead to C, and then you go to G, so that's 3 ways. Or you take one of the 3 paths that get to E, and then go directly to G. That's 3 more paths. So there's a local computation. You add up the values of each of your predecessors, and that's your value. So in what order should we do the evaluation? In topological order, starting at sinks, working toward sources, or in reverse order? Topological order. We start with the sinks and work the sources and work forward. So there it is in symbols. We're looking for that. So we're looking for all the ways, the number of paths from V to everything else. And so there's one way to get to V. Otherwise, you just add up the number of ways to get to everything that comes before you. So again, topologically sort, get the creative spark, realize what local computation you're trying to do, and then figure out what order to do it in at the same time. And it's straightforward. Any questions about this one? Notice that, is this recursive? No, we're not making any recursive call. We're just looking up a previously computed value of an ancestor in the DAG. And how do we know it's been previously computed?
It's linearized.
Because we do it right. We linearized and we did it in topological order. So we're guaranteed to have computed the predecessors beforehand. So this is just showing you. There's a topological sort right there. And using these rules, that gets a 1. The next one to go to is D. We add up all its predecessors, so we get a 1. Then B is going to add up the 2 ones that come before it. Then E is going to add up the 2 and the 1 that come before it. C will just have one predecessor, G gets the 3 plus the 3, F gets the 6. Yeah?
So in this example, to find out the predecessors, that's where we would use the reverse.
Right, you would reverse the graph so you could efficiently determine the predecessors. Okay. All right, this is kind of a contrived one. Cost of a vertex. So every vertex has a price, which is labeled in white. And we want to compute a cost. And the cost is the highest price that's reachable from the vertex, including itself. So why is the cost of D 6? Cost is yellow, the price is white. Why is the cost of D 6? Because C is reachable and it has a price of 6. So anything, the highest, we can look and see that anything, well, let me just ask another example. Why is the cost of G 2?
Because you can reach 2 from G or F.
Yes?
Because its cost is to also half these costs.
Right, so G's cost is 2 for 2 reasons. Its price is 2, and it's also, it can reach a vertex whose price is 2 as well. The largest price in the vertices reachable from G is 2, so its cost is 2. Now why does A have a cost of 8? Yeah?
Because its own cost is 8, and none of its descendants have a higher cost.
Right. So you take the max of the cost of A, the price of A, and the price of everything you can reach from it. And that just turns out to be 8. Okay? So we clear on the definition of what I mean by cost and price. Okay, now, this would seem complicated. What computation are we going to apply to each vertex? It would seem that what we have to do is that when we want to determine the cost of D, we have to look at the price of everything reachable from it, which would entail a search. We don't want to do a search in a DAG algorithm. We want to do a local computation. So what is the creative spark? Yes?
Compare your current node vertex's price to your one of your like child nodes or child vertices, like, and see which one is higher.
Okay, so you got to use the words cost and price correctly. Okay, price are the white things; they don't change. Cost is what we're computing. So I think you're headed in the right direction. What do I have to do to compute? I don't want to do a search. How do I compute the cost of D without having to search the entire everything reachable from D? Yeah.
Just compute check the price of the next.
No, not the price.
The cost of the
cost.
other two.
The cost of D will be the larger of the cost of the things reachable from it, the yellow things reachable from it, and its own price. So why is it sufficient to look at B's yellow number and E's yellow number and not looking at everything that follows it? Yeah?
If you do it in reverse topological order, then you know that what you're looking at, you've already computed the cost of its descendants.
Okay, so we're going to do it in reverse topological order, so that when we go to compute D's cost, we've already computed the cost of B and E. And those costs have baked into it. Those costs, there's no need, if you know the cost of B and E, there's no need to look at the price of anything. Because if there's a big price to the right, it will be incorporated into B or E's cost. So by working backwards, all we have to do for each vertex is take the max of the costs of the things reachable from it and the price of the thing itself. So this is a case when we go backwards in topological order. because the cost depends on successors in the graph, not predecessors in the graph. So there it is in symbols. So let's work this out. There's a reverse topological sort. So we go to evaluate F. So what is the cost of a sink? It's its price. Okay? Now we look at G. So the cost of G is the larger of the price of G and the cost of its child F, its successor F. Both of those are 2. Okay? Now we look at C. What do we take the larger of? C's price, which is 6, and G's previously computed cost, which is the 2. So we get 6. Now what about E?
6.
Yes?
Its price and the cost of C and G.
Right, its price 1 and the cost of C and G, which are 6 and 2. So we take the larger of those, we get the 6. Okay, now it says to do B next. So we're taking the max of its price 4 and the cost of its successor D, which is 6. So we get the 6. D takes the max of 2, which is the price, and then the cost of D and E, its successor, so that's 6. And then A takes the max of its price, and the cost of its 2 successors. And that's how you get the 8. So that's topological sort. An example of a DAG error when we go in reverse order. Yeah?
So I get how you did it, but I still don't really understand what's the significance of price versus cost?
I said it was a contrived problem. So don't try to assign real world meaning to it. Maybe if you thought about it, you could. All right, I want to look at one more example here. No talking near the cabinet. Okay, let's suppose that you got this DAG here. And let's suppose that these are cities, and you have to pay a fee to enter a city. So it takes $10 to enter B, it takes $20 to enter C, it takes $5 to enter D, and let's say it takes $1 to enter A. And let's say you're already in A. You don't have to pay to get to A, you're already there. So what's the cheapest way to get to D? Okay, obviously, we follow that route, and it's 15. So how can we solve this by doing the simple computation in the correct order? We've got a city we're starting from, a city we're going to. How can we compute basically, let's say compute the cost, the cheapest cost of getting, let's make it more general. What's the cheapest cost of getting from A to every city? What's the computation we can do at each vertex? Yeah?
You find the min cost of its predecessors. So you start at A, it's 0, and then you go to B, and then you see the min is.
Okay, so what we got to do is, this is the toll to get into each city. We got the toll to get into each city. We need to compute the cheapest way to get to each city from A. We've got a starting place in mind. So I think that the cheapest way to get to D, here, I would need to know the cheapest way to get to B and the cheapest way to get to C. I would pick that and add 5 to it, right? Isn't that how you would plan the route? So I better have computed those numbers for B and C here before I try to compute the number for D. Now, what's the cheapest way to get to A from A? That's 0. What's the cheapest way to get from A to E?
It's no.
Can't do it, so I'm going to call that infinity. All right. So obviously I can, let's work it forward. Now that we know the cheapest way to get to A from itself, what's the cheapest way to get from A to B? Well, there's only one way. It took 0 to get to A, plus 10 to get into B, so this is 10. Let's consider this one here next. There's only one way to get to, there's two ways to get to B. This one is infinity, this one is 0. This one's infinity, that one is 0. So I take the smaller of the two and add 20. It takes $20 to get into C. Now, what does it cost to get into D? It's the smaller of the two predecessors, 10 and 20, plus 5, so 15. So if you had a big old graph, what order should you be applying the simple computation? In topological order or reverse topological order? Topological order. From cheapest, from sources toward the sinks. And at each place, you just look at the predecessors, figure out which one's cheapest to get to, it's previously computed, and then add the cost of getting into your city. Now, we need a name for this problem. What should we name this problem? Yeah, let's name it AutoSync. Okay? Remember you saw it here. All right, we're done.
Topological